Hello everyone, so in this video, let us talk about a medium level problem from LeetCode. The problem name is minimum genetic mutation. So the problem statement goes like this, that a gene string can be represented by a 8 character long string which has a choice of characters of ATGC. So these are the nucleotides. If you know a little bit about biology, that in a DNA these are the nucleotides, and a gene string they are telling us that it will be 8 character long. Now suppose that you are investigation a mutation. In mutation, any nucleotide will change to any other nucleotide. So what you can see is that in this investigation of mutation, you start from a given gene, let's say from this, and you end up to another gene. Okay, let's say this. And now what you can see is that in each mutation, you are telling that in each mutation only one character is changing. Okay, it is changing from one character to another character. So in this you can see that A is same, C the last, T is changed to A. Okay, so this is one mutation. Now what you can see is that there is a gene bank. Okay, there's a gene bank which stores record of all valid gene mutations. Okay, which means that it stores out what all are the possible gene mutations that can occur. Okay, now what you can see is that you are given a gene bank also. Now you are given a starting gene and an ending gene. Okay, now you have to tell that what is the minimum number of mutations that are required to convert from a starting gene to an ending gene, given that all the intermediate positions, like all the steps that you have to go through to reach from the start to the end, should be in the gene bank, because those also, like those genes that are intermediately or at the end, should be valid, like they should be present in the gene bank. Because invalid genes or or invalid mutations, we do not care about that. We only care about the mutations or the genes that are valid, so that are stored in the gene bank. And if there is a possible path from the start till the end such that all the genes are present in the gene bank, then it is a good, like you can see that you just have to count out how many number of steps are required, else you have to return -1. That's the overall problem statement. Now you can see that from this to this, you are going from this to this state. Now in this, the last state is changed, like the last character is changed, and this last gene is also present in the gene bank. So every step that you do from the start till the end should be present inside the gene bank. Now that's the overall problem statement. So like you can see again, from here to here you want to go. Now all the different genes that are possible are present in the gene bank. You just have to tell that whether it is possible to do that. Now what you can directly observe from this statement is that you have a particular gene bank and you have to only do the iteration on that gene bank. So you have to somewhat make a graph out of that, because so what you can directly also understand is that from every position you can go to another position by doing one mutation. Okay, so what you can directly understand from here as well is that what you can do is, let's say that you have a starting position of AA. I'm just talking about 4 characters. Okay, I will only talk about 4 characters, but you can extrapolate this information to 4 characters or 8 characters or any number of characters which is in the problem statement. It has only 8, but for a simple understanding, let us take about 4. AATT. Now from this, you can go to a state that is ATTTT. If all of these genes are present inside the gene bank. So I'm building this type of graph which tells us from which gene I can go to which gene, given that only one character is changed. Okay, now from this also I can go to one more gene state. Let's say it is present in the gene bank, AATG. Now from this, let's say there's one more position that I can go to is AGTG. So only one character should be changed. Okay, so all of this is some sort of a graph. Now let's say that you start with AT, and then, okay, not A, C. This is the position that you want to start to. So what you can do is that from this position, what is the intermediate, so you have to first understand that from this state, what all are the genes that are present in the gene bank, that is just one step ahead, or like ahead of this particular gene, because this is the starting gene I want to go to. Any other gene, we have to present that it should be present inside the gene bank. So the other cases can be that this can be flipped, this can be flipped, this can be flipped, this can be flipped. So these are different positions. And the first one, I can actually say that I can go to this state. Okay, then I cannot go to this state because okay, I can also go from this to this state as well, because only like G is changed. Can I go to this state directly? Can I go to this state by just one change? No. So these two I can connect to the starting like the starting gene, and then you can directly do a BFS, because it's just a minimum distance between two given nodes inside a graph, which is just a BFS. So you just have to do a BFS from this node to the node, whatever node you want to reach to. So you just do a BFS. At any point, you just check that whether the ending node I want to go to is present here. Then you can directly do. Because these genes are pretty small, you can directly do a complete comparison of 8 like characters, like whether they're completely matched to the gene I am on or I want to go to. So you can directly do that. And that's it. You will just do a DFS. We first make a map from the gene bank, then you insert the gene I want to start from, then do a BFS over that, and you will keep on doing the BFS, counting out how many number of steps you are doing to reach the end state, the end mutation. And if it is possible, then return the number of steps that you have taken. If it is not possible, return -1. That's it. That's the overall problem statement and the solution part. Let us move on to the code part to how you will do this. So it will start from here, the minimum number of mutations. This is n. This is the adjacency matrix, that is the, or adjacency list I can say, sorry, which is used to build this whole graph. So this is the adjacency list, which is a particular string is mapped to how many different strings from a particular node, how many different nodes I can go to. So what I'll do is that I will iterate over every possible pair of nodes, and so I and I plus 1. Okay, so this is just iterating over every possible nodes to just make the adjacency list that from which node I can go to which node. So I can go a particular node to different node. Like if I'm on node A, I can go to node B if and only if there's only one number of mutations. Okay, so this is the difference. This is a difference function that will iterate over both of these strings, and just check that the number of different number of characters between these two strings. Okay, so this is A and B, and if the number of difference is only one, then it is a possible mutation. I can go from that particular node to another node. So I will just check out that if it is possible, then I will just make a let's say an edge between these two nodes of this particular string. Let's say the ith node to the jth node and the jth node to ith node. So it's a bidirectional, okay, path. So that's why I've created a adjacency list like this manner. Now what you have to do is that from the starting node, again you have to check that what all nodes you can go to. So what you can do is, again you will take the starting node, that is the start, from which I want to start my mutation, and iterate over all the other nodes, again those n nodes, and just check that whether this starting node is connected to all the nodes, like which all nodes I can connect this starting node to, because that's the starting node. And what I'll do is that I'll again iterate over all the nodes, check with this difference function that will just check that whether these two nodes are compatible to be called a mutation. By mutation I means that they should be only having one character change, and this function is just doing that. Just check that if it is possible, then we'll just again make a edge between the starting node and the given node in the gene bank. Now we have the complete map with us, so we will just do a BFS from the starting node. We'll make a queue of strings, push the starting node, okay, the starting, you can say the starting gene, and then and to store that whatever genes we have iterated, we don't double iterate over all them, because we have been making a bidirectional graph. That is where set comes into play. So we'll also insert all the nodes that we have iterated to push inside the set, so that we have to know which genes we have iterated over, which genes we have not iterated over, and we have inserted that also. This is the total number of steps we will take from going from start till the end. That is the answer. It's just a standard BFS. Keep on doing this iteration over this queue until it is not empty. Find out the size of the queue, iterate over all the particular level or the traversal, so over all the nodes that we have seen till now. Okay, then what we'll do, then iterate over all the edges or all the connected nodes to a given node again. Okay, and what we'll do is that whatever node I am on, I have two things. I have to push that inside the queue and the set, given that it is not already iterated over. So if the count of that particular node I'm on, if it is 0, which means that it is not iterated over eventually like previously, then only I will do this operation. If it is already iterated over, I will not do that. And then I will keep on doing this and increment the answer for every level. And the end, if at any state I find out the the final node or final state I want to reach to, if I insert that inside the, you can say, set, which means that I have already iterated over that particular node, and return the answer, which means the total number of steps that I've taken, the minimum number of steps that I've taken to reach that particular node from the starting node. Okay, this is just the BFS. And in the end, if I'm not able to reach that particular state, or maybe that is not present inside the whole gene bank or in the whole graph, then the answer is -1. That's it. That's the logic and the code part for this particular problem. If you still have any doubts, you can mention down in the comment box of this particular video. I will see you in the next one. Till keep coding, and bye.